And with that, we will get started. Well, good evening, everyone. I'm Sarah Kravitz. I'm the Boston Beck Chair, and thank you for attending our presentation today. Just a couple of housekeeping items before we get started. To receive AIA credits, I just posted in the chat a link to a Google form where you can enter your information, and then we'll follow up with the AIA credits. Also, I encourage you to join our LinkedIn group for any upcoming events, or you can also log into the BSA website and get on the mailing list for also all of our upcoming events. I ask you to wait to ask your questions in the chat to the end of the conversation, unless it's something to clarify, what material is noted in the detail or something similar, then I'll politely interrupt Laura, but for more in-depth questions, please save them to the end. And without further ado, I'd like to introduce our presenter. So Laura Kennarth is a registered architect and a senior enclosure technician designer at Walter P. Moore in the Los Angeles office. So thank you for joining our Zoom meeting. I'm glad that we can have a presenter from all the way across the state. She is an impassioned advocate for building data management and for high performance facades. So much so, she's also a co-founder of the Los Angeles chapter of the Carbon Leadership Forum. At Walter P. Moore, she oversees the delivery of highly complex building envelopes in 4 different continents and applies her knowledge and experience to using data to address embodied carbon in the built environment. So without further ado, thank you, Laura, for presenting today. We look forward to hearing about what you have to say about embodied carbon.
Thanks, Sarah. I will share my screen. Can you guys see it? Awesome. So I'm going to hopefully build a little bit on the presentation that you guys had last month that kind of introduced all of the alphabet soup of GHGs, GWP, EPDs, LCA. So this presentation is assuming you have somewhat of a baseline knowledge of that stuff and getting a little deeper into how that actually applies to the building enclosure. So got a couple of learning objectives that we're going to go through in the presentation, and I will kind of reintroduce some of those concepts from the last presentation briefly, and then really get into it. So start off with very, very quick Carbon 101 in case anybody missed last time. So we've all probably seen this graph or something like it. We know that building operations are responsible for about 28% of global CO2 emissions. But there's another piece of those emissions that we haven't talked about so much as an industry and as a profession until more recently. And that's the CO2 emissions that are from building materials and construction. So that's what we see in yellow in this chart. So what does that mean? Well, we've talked in the past a lot about buildings' operational energy use, but we really want to think about the whole life carbon of a building. So that starts well before the building is built and occupied with the extraction of raw materials that are then made into building products, the manufacturing of those products, the transportation of them to the construction site, the actual construction, and then at the end of the building's life, the deconstruction and disposal of those building materials. So we're kind of broadening the way we're thinking about carbon in buildings. And so when we talk about embodied carbon, we're talking about the carbon that's embodied in those materials, and that's all of the stuff in yellow in this diagram. So the only piece where we start to talk about operational is in blue. So we're talking about all this yellow stuff. We also want to talk about the time value of carbon. So this is a really awesome chart that the AIA and the CLF put together for their embodied carbon toolkit for architects. And it's basically showing a timeline of a building's life and the carbon emissions that happen in each year of the building's life. So right at the beginning in year 0, we have this big, tall yellow bar that is the upfront or embodied carbon. And that's what I was talking about, all that carbon that's associated with building materials and the construction process. And then throughout the building's life, it has in these blue bars operational emissions, and those are hopefully going down over time because we're cleaning up our energy sources, we're cleaning up our electrical grids. But we also have periodically throughout the building's life, more embodied carbon you see in year 15 and year 30 as things are maintained, as things are replaced. We do have more embodied carbon happening then, but really you can see a lot of this carbon is happening upfront at the very beginning. So if we want to meet the near-term goals of the Paris Agreement, like we've really got to look at what's happening now in terms of embodied carbon. So that's kind of the 101. What does that mean for the building enclosure? Well, we can start to look at enclosure materials. So this is the embodied carbon materials pyramid, just kind of like the food pyramid, where the things at the top of the pyramid are things that are highly carbon intensive and maybe you want to try to use less of, and things at the bottom of the materials pyramid are less carbon intensive. So where do we find enclosure materials on this pyramid? Well, things like aluminum that are used in curtain walls, glass, insulation. You can start to see they're really clustered at the top of the pyramid. So that's why it's really important to think about this when we are designing building enclosures. But we also have to think about not just materials, but the whole system, how they work together, because you can't always swap out a material one for one without thinking about how that impacts the rest of the system, because everything's performing a function and everything contributes a different amount of embodied carbon to the system as a whole. So that's where the conversation around carbon and enclosure starts to get pretty complex. So how do we measure this? How do we understand this? How do we move forward and do something? We can start by doing life cycle assessment, which, as you guys learned in the last presentation, is the evaluation of the environmental effects associated with doing something from the initial gathering of raw materials all the way through until those materials are either returned to the earth through disposal or hopefully recycled and reused in a new way. And we can use there are a number of tools that are available to us as architects and designers of the built environment that we can use for that we'll get into in a little bit. So what does LCA do? Well, this diagram that I showed you at the beginning about the life cycle of building products is actually formalized into life cycle stages that are evaluated when we do LCA. So starting with that extraction and manufacturing, that's the product stage, followed by transportation to the construction site and the actual construction process. So that's another stage. Then we have the use stage, which can include building operations, but it can also include the repair and replacement, refurbishment of parts of the building. Finally, deconstruction and disposal is in the end of life stage. And then there's something we call module D, which is information beyond the boundaries of the system. So the chart on the top is kind of the usual system boundaries when we're talking about a building and we're talking about a building's life cycle, but sometimes there are additional things that happen. So for example, recycling of something, if you take out a curtain wall and you send the aluminum for recycling, it has a new life. So that could be credited back toward your building or credited toward the next building it's used in for the recycling. So that's what happens in module D. There are also several different environmental impact categories that we look at when we're doing LCA. The big one that we're talking about when we talk about embodied carbon is global warming potential, or GWP. But there are a number of other potential environmental impacts that we need to consider. So in order to get GWP down, you might see increases in some of the other impacts. So that's why we have to look at all of them and we have to balance all of them when we're making our decisions. So we have a building, we have some materials that we maybe want to use. How do we know what the environmental impacts of these materials are? We get that information from an environmental product declaration, or EPD. And the purpose of that is to give information about the life cycle of a building product, or any product really. And the purpose is to enable comparison between multiple products that fulfill the same function. So functional equivalence is really, really important to consider when we're making decisions and when we're comparing the environmental impacts of materials. So to dig more into EPDs, we can say, going back to the food analogy, that an EPD is kind of like a nutrition label for a building product. So on a nutrition label, you have a serving size. In an EPD, you have a declared unit. So in this case, my EPD declared unit is 1 metric ton of glass. On a nutrition label, you have the quantities of certain nutrients in the food. And in an EPD, you have quantified different environmental impacts. So coming back to our life cycle stages, an EPD only considers the product stage. So that's the raw material supply, the transportation to the manufacturing facility, and the manufacturing itself. All of the stuff that happens beyond that, we don't know from an EPD, and that's one of the things that our life cycle assessment software will help us with, because it uses other data sources to fill in this other information. So there are a couple of different kinds of EPDs that you're going to see as you're looking at building products. There are 2 kind of major categories. There's an industry average EPD, and then there's a manufacturer or product specific EPD. So like on the left here, we have an EPD that's just for flat glass, like all of it that's produced in the US or in North America. But we also have a vitro EPD for processed glass, a little bit different. And I have a Harman EPD for a curtain wall system. So these are both manufacturer EPDs that cover specific products. So you can see already that these aren't necessarily comparable one-to-one across the 3 of them, but they all provide us with valuable information if we are specifying and evaluating options for a curtain wall. So digging a little deeper, we will have a product definition in each of these. So in my industry average EPD that's from the National Glass Association, it's an industry average of flat glass, and it includes clear and tinted and low iron glass, but it doesn't include any coatings or any IGUs or anything, versus our vitro EPD that's manufacturer specific, that includes coatings, and it also includes IGUs. So again, this is really important to know what the EPD you're looking at covers, so that you know whether or not you can compare it to other things. And again, if you can't compare 2 things directly, your LCA software can also help you with coming up with different ways to look at a project. So we also have to look at geographic scope. So if my project's in the US, either of these EPDs will apply to me. The industry average one is for products sold in the US. This vitro one is the average for all of Vitro's products that they sell all over the world, but that covers me in the US, so that's okay. Next, we will get into the declared unit. Again, these 2 aren't necessarily comparable, but my LCA software can help me by converting things into comparable units. So on the left, I have a metric ton of glass, but on the right, I have a square meter of processed glass. And I have different kinds of processed glass that I can look at. And finally, both of these are still sort of averages, right? My industry average EPD is for the whole industry. But if I look at, for example, the double pane IGU in my manufacturer specific EPD, it's actually an IGU that consists of 2 average panes of glass. So an average is the production weighted average from this manufacturer. So this EPD could be really useful for comparing 2 different manufacturers, because they're probably both using a production weighted average, but it's not necessarily for one real specific product that exists. It's kind of the average of all of their products. So there's imperfect data when we are looking at environmental impacts. So it's important to understand the data you're looking at and how you can use it, because all of this is still useful, even if it's not every specific different version of every single IGU you could have. So how do we do this in the context of a project? There are a number of tools that are available to us in this industry to measure embodied carbon and to do life cycle assessment. So the one that I primarily use is Tally, which is a plugin for Revit. And it's really great because you're probably already modeling in Revit, and you can use your Revit model to get quantities and to assign attributes to the material in your Revit model that will then pull information from EPDs and life cycle data to tell you what the impacts are of your design. There are a couple of other tools. There's also One-Click LCA and Athena, which are also tools that will do a similar thing. And there's another tool you might have heard about called EC3, or the Embodied Carbon and Construction Calculator. That one's a little bit different because the tools on the left will do a whole building LCA, which have all of those life cycle stages that we talked about, where the EC3 tool only looks at EPDs, so it only looks at the product life cycle stage. So we call it more of a supply chain accountability tool when you're comparing one specific product versus another specific product. And again, coming back to our life cycle stages. So all of these stages that I have highlighted in orange are what are required to do a whole building LCA. I also want to talk about, when we're talking about life cycle stages, the importance of durability of the products you're specifying. And that's where this B use stage comes into play. So we have use, we have maintenance, repair, and replacement. So you could be looking at two different products. In my example, option A has a little bit higher GWP than option B, so it's maybe a little bit worse. But my building life is 60 years. Option A has a 20-year expected lifespan, and option B has a 30-year expected lifespan. So if I'm only looking at that EPD, if I'm only looking at the initial product as opposed to doing a whole building LCA, I might think, oh, well, option B is the obvious choice. But throughout that building's 60-year lifespan, product B is going to be replaced twice, where product A is only going to be replaced once. So that's why it's important to consider using the right product for what you're doing and thinking about the longevity and the durability of that product. So in our whole building LCA, we have our building, we have our Revit model, maybe in the case of Tally, we are using a tool like Tally to apply attributes to it. And then we're getting some results about our environmental impacts in those different impact categories that I told you guys about earlier. And most of the time what we're doing here is we're starting with a baseline, maybe how we would have designed this building if we weren't thinking about embodied carbon or if we weren't thinking about environmental impacts. And then we start to make some adjustments to our design to see what we can do to optimize for reduced impacts. And we can see how that compares to the base building. So we're always doing comparisons. We're always trying to optimize to do a little better than we would have done otherwise if we weren't thinking about this. The other thing we can do, if, like me, you are a practitioner who only works on a specific portion of the building, like I'm an enclosure consultant, so the structure is not really something that's always under my control, although since I do work at a multidiscipline firm, I do work with our structural engineers and we collaborate together to work on whole building LCA. But let's say I'm on my own on a project, can't do the whole building, or I don't know enough about the whole building. I can start to look at just the systems that I'm specifying and do an LCA at the level of a system. And I can try to optimize that enclosure system that I've got to get some reductions just within that system. And then I know that, okay, however many square feet of this facade system I have on the entire building, I get to multiply my reductions by that much. So even if you don't know what you want to do for the whole building, you can still start to look at this as at a system level. So to do that, I'm going to show you guys a couple of case studies, and they would look at kind of very different stages in when you're designing and the kind of things that you would look at. So the first one I'm going to talk about is just about comparing different materials or different systems overall in the early concept stage of a project. So I don't necessarily know yet like what products I'm going to be specifying, like what specific manufacturer's products I'm going to use, but I do know generically, you know, one type of system versus another. So this was a concept phase for a design competition that we worked on with BNIN. It's for a building in a higher education campus, and they had 3 different concepts for us to evaluate. So they had kind of 3 different, very different designs that would lend themselves to different types of facade systems. They had a materials palette that they knew they wanted to go with. They looked at the existing campus, what's there, there's a lot of brick. And then they proposed some material palettes that they would consider using on their design. So they looked at some different brick options, some kind of detailing. They looked at some terracotta, some like shading fins, that kind of thing. So what we wanted to do was help them put together a palette of actual facade assemblies that they could use for this project. So there's a number of different ways that they could achieve any of these kind of finishes, these design intents that they want to do. We looked at 2 different glazing assemblies. We looked at 4 different brick assemblies, and we also looked at like a terracotta green screen for the opaque walls. So to get the brick finish they want, we could do like a thin brick on a precast sandwich panel. We could do a thin brick on a thin shell precast panel to get kind of a mega panel system that could be installed really quickly. We could also look at thin brick on an insulated metal panel or just a conventional brick green screen. And so those are going to be more stick-built type systems. So already we're not just thinking about materiality, we're also thinking about constructability. And so we took a little swatch of each of those, little like 100 square foot swatch, and modeled them in Tally and looked at how they stacked up against each other. So this is a lot to look at. This is all of our environmental impact categories, but we really wanted to focus for this project at first on the global warming potential or the embodied carbon. So now we have a comparison that we can look at. And I'll primarily talk about what we did with the opaque wall assemblies. So for each of the ones that involved concrete, we also looked at 2 different concrete mix designs, sort of typical mixed design and a lower carbon mixed design, to see if maybe by using low carbon concrete, we could get some of these heavier systems to be closer to some of the lighter systems in terms of embodied carbon. And we just wanted to see, okay, what are our highest and lowest embodied carbon options? Again, that's not going to be the only thing driving selection, but we want to know where we're at. Next, we started looking at, okay, we have 3 actual design options here, and they might lend themselves to different constructability approaches. So our options 2 and 3 actually have, at least for a portion of the building, the facade set back from the slab edge so that they could have exterior circulation. So that's not really going to lend itself so well to a mega panel system. We're going to want to do one of our stick-built options on these ones, at least for those portions that are set back. And then for our option 1, we can start to look at maybe our mega panel systems. So the option 1 was also kind of interesting because it had like a sawtooth shape to the facade. It's a little hard to see in this rendering. So it had a little bit of geometric complexity to it as well. Our first 2 options had primarily brick as the materiality, and the third option was primarily terracotta for the opaque enclosure. So each of these designs has different systems that it wants to use. So to get a baseline, we started assigning from our palette of facade systems as we would if we weren't really thinking that much about carbon yet. So like our first option got mostly our mega panel type systems. Our second option got like a combination, and then the third option was mostly like the terracotta rain screen, which you might remember from the couple slides ago was the lowest carbon of the options when we checked our swatches. So what that gave us was 3 different baselines. And we could look at, okay, why is option 3 better than option 2, which is better than option 1? And we could start to think about what is driving that embodied carbon. Well, first of all, option 1 had the most of the sort of higher carbon intensity systems. Option 2 had kind of a mix, and option 3 used primarily a lower carbon intensity opaque facade system. So that's one factor at play. The other factor is just that option 1 had the sawtooth facade, so there's more facade there. There's more like area of facade on that building versus 2 and 3 where they pulled the facade back to the slab edge. There's like a little less of it. But maybe we can do something by changing the types of systems we're specifying to get option 1 down a little bit closer to 2 or 3. So we started to think about, okay, what changes can we make to get this a little lower? And so we were able to get probably about a 12% reduction in option 1 and like a 10% reduction in option 2. So that was pretty good. All we had to do was kind of think about it a little bit and make some trade-offs.
So I do have one quick question, Laura, on that note. Does your comparison between stick-built and panelized take into account construction waste?
At this stage, it's not really specifically taking into account construction waste beyond like what's built into the LCA tools. So the LCA tools have a certain amount of construction waste like built into them for different materials.
Okay.
But that's a great point. If we were a little further along than concept, I would definitely look into that in more depth. So now I'll get into the second case study, which is a little different. This is starting with a system that we already know what the system is, and then looking at how to get optimizations within that system. So this was a little LCA that I worked on with Clark Pacific for their thin shell precast facade system. And so we already have the system, we already know what it is, but they wanted to understand, first of all, where they were at in terms of embodied carbon and if there was anything they could do to optimize. So we have a thin shell precast facade, it's got spray foam insulation, it's got a steel frame, and we included the interior gypsum board finish. And so when we look at the system, one of the things we wanted to do was find the hotspots. So we can look at, okay, which pieces of the system make up the largest share of the overall mass of the system, and that's going to be concrete. We can look at which of these things make up the largest portion of the GWP. Again, concrete, because it's the most of the stuff that is part of this wall system. But if we look at the mass and the GWP together, we can start to see some other hotspots. So our steel, for example, is only about 11% of the mass, but it's 29% of the global warming potential. So it has an outsized impact for how much of it there is in the system. And the same thing with the spray foam, it has quite an outsized impact for how much of it there is in the system. So we can start to look at that. We're going to start with the concrete because that's responsible for the largest overall amount of GWP. And when we look closer into concrete and we look at what's in the concrete by mass versus by global warming potential, we know that the number one thing driving the global warming potential of concrete is Portland cement. So anything we can do to modify the concrete mix design so that it uses less cement is going to help us on our GWP. So the first scenario or optimization we looked at was understanding what the impact would be of changing the concrete mix or just using a slightly better concrete mix. So we were able to get somewhere around a 5% reduction for the overall system just from using a better concrete mix. We also looked at the insulation options. So insulation is a really big one, especially with spray foam. So there are two different categories of blowing agents you can use with spray foam, HFCs and HFOs. So the older HFC blowing agents have a really high global warming potential. And so you can see in my graph here, option 1 and option 3 are both HFC blowing agents, and option 2 and 4 are both HFO blowing agents. So you get a pretty dramatic reduction just by changing what blowing agent you're using. And the HFCs are starting to get phased out. I believe California has actually banned them, although they haven't necessarily been banned everywhere yet. So that is a good place to target for looking at GWP. And then the third scenario we looked at is not necessarily an optimization you would do, but rather a way to understand how changing the configuration of the facade system affects the GWP. So we looked at just a plain solid precast panel, as well as a couple of different window to wall ratios. Obviously, those are going to have an effect on the design, on the operational energy usage. But we can also start to look at, okay, when we mix different systems together, what does that do to our embodied carbon? So this one's kind of interesting because the more glass you put in, the more the mass of the system went down, but the GWP didn't necessarily follow. So that was kind of interesting just to know. You can look at different systems individually, but then when you start combining them in different ways, you'll have to see what that does overall to the GWP. So those are some ways that you can look at the system level. Coming back to the whole building level, we can get into how life cycle assessment is used in LEED. So if you are going for LEED points, you can get points for doing life cycle assessment. And it has to include at minimum the structure and the enclosure for the building. You can also include things like interiors, MEP systems, but the very minimum is structure and enclosure, because a lot of the optimizations in LCAs that I've worked on for LEED have come from mostly the primary structure, but there are also some opportunities in enclosure. So in LEED V4, you can get 3 points for doing LCA if you can, and you'll do 2 options. So like I showed in that slide a little bit ago, you do a baseline building that would be kind of the version of your building if you weren't really thinking about carbon, and an optimized version. And you need to show between the baseline and your actual designed version 10% environmental impact reductions in at least 3 categories. And one of those categories has to be global warming potential. So GWP in red here, you have to get 10% reduction. Any of the other 2 categories, you also need to get a 10% reduction. And the other remaining categories might go up as a result of reductions in GWP, but they can't go up by more than 5%. So we don't want you to get a huge reduction in GWP, but then like a 30% increase in one of the other categories. We want to kind of keep everything balanced. So that's kind of the only option in LEED V4. In LEED V4.1, there are a couple of options for LCA. You can get 1 point just for doing a whole building LCA to understand what the environmental impacts are. This one doesn't necessarily involve option comparison. Part of the reason why we do this is because as an industry, we really need to get good data as to where buildings are at in terms of GWP. So the more we can incentivize more projects to gather data, the better, because then we know as a whole what our baseline is. You can get 2 points by getting 5% reductions in 3 of the categories. Again, one of them has to be GWP. And again, you can't get more than a 5% increase in any of the remaining categories. You can get 3 points for 10% reductions in 3 categories. Same rules, has to be GWP. Other ones can't go up by more than 5%. And you can get 4 points by showing a 20% reduction in GWP and 10% reductions in any 2 of the other categories, and also using salvage materials in your building. So this one is really to incentivize reuse in addition to reduction in global warming potential.
So Laura, I have a quick question. In LEED, what is the reduction compared with? Is there some kind of baseline? So would that be the model that you did without any like carbon incentives?
Yeah, you get to define your own baseline for LEED. There is not yet enough data that's kind of standardized across the entire industry that you could define like an industry-wide baseline. So it's relying on the designers to establish their own baseline. So, I mean, when you're establishing your baseline, you want to do it in good faith. You don't want to give yourself a really terrible design so you can show reductions. You want to do a reasonable baseline, but maybe what you start with at the beginning of SD or whatever, and then you can start to optimize from there. So there's not a lot of definition in how the baseline is defined.
Thank you.
So the next thing you'll want to think about is when you should perform full building LCA. The earlier you do it, the easier it is to make big system changes. If you're looking at structure, like deciding between concrete or steel or timber is something you're going to do at the very beginning, you're probably not going to change structural systems in CD. So the later you get in design, the more challenging it becomes to make changes. And then by the time you get to construction, you're really just limited to procurement optimizations. So you're thinking about, am I buying this material from supplier A or supplier B? Maybe there's a little bit of a difference in impact depending on who you buy the material from, but you can't really change from one material to another, most likely. Which also brings us back to the EPDs and when you should use one type of EPD or another. So at the beginning, when you're in like concept design and you're comparing completely different materials, you probably want to use an industry average EPD because you probably don't know yet what manufacturer you're going to use, what supplier you're going to use for that material. So the industry average EPDs are really valuable when you haven't committed to a specific supplier, when you just want to play around with your design and get a lot of ideas. And then once you start to get down to either you, the designer, are specifying a product or a manufacturer, or in construction, when the contractor is actually procuring the materials, that's when you want to start to get into product specific EPDs. And you can always use product specific EPDs earlier. Just know that it reflects a specific product or a specific manufacturer. And if you go with something different, it might not be accurate. So I will also give you guys some tools and resources that you can find for building embodied carbon literacy. We all, I think, have a sense of when we're making design decisions, what the cost implications are of those design decisions. If a change is going to be more expensive or less expensive, we don't always have a good sense of the impact that those design decisions have on embodied carbon. So the idea is to start to build your literacy, start to build that sense, so that when you're making design decisions, you can think, ooh, this might increase the embodied carbon. I should go look into that a little bit further. So like I mentioned, the construction materials pyramid is really great. The downside of it is it basically allows you to compare materials only by mass or by volume. And all of these materials are used for very different functions in very different ways. So functional equivalence is not really covered here. You can also look at places like the Carbon Smart Materials palettes. This is a graphic from that site that has comparison of different insulations. So that's really great because we're starting to get into functional equivalence, but we're only looking at individual materials and not systems as a whole. Another really neat tool that Payette Architects put together is called Kaleidoscope, and this is available on their website. And this is actually looking at full wall assemblies, and I think they have roof assemblies too. They've slowly been adding to this tool since I started looking at it. So always being updated, but it looks at full assemblies and you can compare different exterior wall finishes to each other and understand how each component of that wall assembly contributes to the overall embodied carbon. So this one's a really great resource to do like quick comparisons or just to get a general sense of how different systems stack up against each other. If you're doing it for a project, it's really ideal to actually do the LCA to understand what you're specifying and the way that you're using it, what environmental impacts will actually come out of that. There is also the Embodied Carbon Toolkit for Architects, which has 3 volumes, the sort of intro to embodied carbon, how to measure and do LCA, and then some tips for strategies for reducing embodied carbon. So this was put together by the Carbon Leadership Forum and the AIA, and is also a great place to start. Another report that's out there that I think is pretty cool is Walter P. Moore did a stewardship report, and we did a number of different articles that cover different aspects of embodied carbon in the built environment. So this is also a great introduction to some of the issues that are at play when we're talking about embodied carbon in buildings. So I will leave some time for questions, and I'll wrap up with a challenge to everyone on the call, which is to do something on every project, not just the ones that have awesome LEED goals or awesome sustainability goals. Always be thinking about it when you're designing and ask yourself, where's the carbon?
Thank you, Laura. I appreciate that. I like the question. Where's the carbon? We'll definitely take that moving forward. But before we wrap things up, we do have a couple of questions. One is from Greta, and her question is, how is the performance of the material addressed in the whole building calculation in terms of how it will impact operational energy of the building?
So a lot of times the whole building LCA will not necessarily take into account operational carbon. There are LCA tools that allow you to evaluate it, but like the energy model and the whole building LCA are two different things. They can inform each other, but it's not really part of the whole building LCA process.
Okay. That's good to know from when we're, I guess, comparing different types of insulation, that it's not going to take the R value into consideration.
So like when you're setting up the whole building LCA, you should put, like if you're comparing alternatives, you as the LCA practitioner are going to set up, you know, if I'm looking at, I don't know, mineral wool versus spray foam or something, like I'm going to make sure that they have equivalent R value when I set up the LCA model, but the tool isn't necessarily going to do that for you automatically. So that's why like it's important as an LCA practitioner to make sure that you are using functionally equivalent systems.
Okay. We have another question from Richard, and he asked this fairly early in the presentation, but he says, what does declaration type, example, business to business, mean?
Okay, so the environmental product declarations are defined by an ISO standard. And so the declaration type is, they have to tell you what it is as part of the ISO standard. So the business to business means it's being put together by one business, the manufacturer of the product, for another business, say the designer or the contractor, to use in their LCA.
But why would it be different? I mean, if you, the life cycle carbon use is not going to change if I'm reporting it to a person compared to a business, is it?
You know, I don't know the ins and outs of like the different types. I just know that all of the ones that I've looked at are of that type. There may be different standards for EPDs that are directed at consumers, but I don't really know enough about it to give a firm answer on that.
Okay, thank you.
We have a couple questions from Steve. So when considering embodied carbon savings versus operational carbon savings, do you place a specific premium on reducing embodied carbon since the benefits are immediately realized? If so, what is the premium? Is there a good rule of thumb?
I do not know of a good rule of thumb for that. You can look at like that diagram that I had at the very beginning with the building's carbon over the life cycle. You can look at something like that and say, okay, if I have a 10-year climate goal and actually I want to use some lower carbon thing now, like you can weight it that way, but I don't know of a standard for necessarily how to weight those things. I've seen some research published on how to weight the different environmental impacts against each other, but less so for current versus future emissions.
So it kind of depends on either like the owner or the, I guess, the goal that you have, whether it's to reduce your occupancy carbon or your building carbon, and kind of finding a way to meet both of those, but they're kind of separate in how you analyze them.
Yeah. Yeah, and it's also important to note that like you don't have to, a reduction in embodied carbon doesn't necessarily mean an increase in operational carbon. That's why we're trying to use functionally equivalent systems, like the same amount of insulation, but maybe a different type, versus like saying, oh, it's okay if we reduce the insulation and increase the operational emissions.
Okay. Does anybody else have any questions? I will post in the chat one more time for anyone who would like to receive AIA credits to fill out the Google form link.
I guess I have a question related to a comment I put in the chat. First of all, thanks for a great presentation, Laura, and for very systematically going through all this material. And I realize that in the design process, this should never be the one and only criterion for making decisions, but it's important to have a systematic way to do it. But I noticed, I didn't look at obviously the details, but the three facades that were being compared, two of them, the facade was being set back from the slab edge. So that means there's going to be a huge thermal bridge where the concrete goes from the outside to the inside. And it can be, I mean, there are systems and details to minimize that, but that would be one example to me of operation, losing it, you know, increasing the operational energy. Maybe the embodied energy was reduced, but it seemed like if it's a decision that's made early in the project, then people should know they're going to have to detail that thing, or, you know, it's a complex.
Yeah, absolutely. And I think that project, there's, with all of this stuff, there's a lot more going on in the decision-making process than just embodied carbon. It was more of exploring, okay, why is this one worse than the other in terms of embodied carbon? And like those three examples were obviously not necessarily functionally equivalent. They're very different designs. So it was less of a saying like option A is better than option B, and more of a exploration to understand where we're at in terms of embodied carbon. It was also in a very mild climate, that project.
Yeah. So maybe. Actually, one other comment. It seemed like in listing the different impacts, life cycle impacts, I didn't see water usage mentioned, but I believe that is one of the impacts that's included in a complete life cycle analysis. And I think water is going to become a pretty precious commodity in the future. And I hope people are also thinking about the in the same way as embodied carbon, what impact on water resources.
Mm-hmm.
That's just a comment, but
yeah. So there, like, eutrophication takes into account in some ways impact on water resources, but not necessarily like water use in the building or related to the manufacturing process.
Yeah, I was thinking the manufacturing process.
Mm-hmm.
Also on that note, we have a question from Kat. What do you think is the next frontier for embodied carbon reductions?
Thanks, Kat. Kat is my colleague. Kat with the hard question. I really think that we need to start thinking about this on all of our projects. So I think that like structural engineers are kind of in some ways ahead of the curve on embodied carbon. So there's the SC 2050 challenge, which is for structural engineers to get to net zero by 2050. So structural engineers are really doing a lot of LCA, looking at alternatives for different concrete mixes, for example, to try to reduce embodied carbon, because because the structure is the biggest contributor to the overall embodied carbon of a building. But I really think that we all, like all designers of the built environment, need to build this literacy for the systems that we're designing, and to just really be thinking about it as we're making design decisions. So you're thinking about schedule and cost. Okay, now you're thinking about like schedule, cost, and carbon.
That's a good point. I didn't think about how much influence structural engineers have on embodied carbon. Kat says, thanks, Laura. Well, thank you, Laura, from all of us for this amazing presentation. Within a week or so, this will also be posted on our website. So if you want to go back and look at her slides, especially the few that have tools and websites that you can reference, definitely check on our website. And also along those lines, you can see the presentation before Laura that talks a little bit more about the broad overview of what embodied carbon is and LCAs. So that way you can combine the two presentations and have a more in-depth knowledge about embodied carbon and how you can incorporate it into your own designs. So thank you so much, everyone. I really appreciate you coming. Enjoy the rest of your evening.